Okay guys, so we're going to look at 2020 Leaving Cert Physics question 3, which is the experiment to determine the speed of sound in air via resonance tubes. So they determined this by measuring the lengths L of a narrow column of air when it was vibrating at different fundamental frequencies, and they recorded the following sets of data. So as you can see, they gave us 6 sets of frequencies with 6 corresponding lengths. First thing they asked us to do was draw a label diagram of the apparatus used and how it was arranged in this experiment. So again, what's important is it's a label diagram and that the arrangement is drawn correctly. So what we'll do is I'll just move down, give myself a nice bit of space here. And as I've said before in previous videos, there is no such thing as a diagram that is too big unless it goes off your page, but there is such thing as a diagram that is too small. Again, all diagrams are always drawn with rulers. And again, you should have practiced these diagrams so many times that when you look at your Section A questions, first thing that pops into your head when you read the title is going to be what the diagram should look like. So first of all, that's my resonance tube. I'm going to draw that now sitting inside a graduated cylinder. And just move that down so it doesn't move off camera for you. I'm going to draw that line coming across. Okay, and I am going to draw the water level going across there. Okay, and the last thing I need to draw is just my vibrating tuning fork sitting at the top. Okay, so there's your diagram in the correct arrangement. You do need to make sure that you show what the labels are. So the first thing I have is my resonance tube. And just a quick little line to bring it to here. I have my graduate cylinder. My line goes to this here. Obviously, like we said, it is sitting in water. So I can just kind of label it into the water. This is my tuning fork. And one thing that is very important is that you label the distance L that you measure. So the distance L is from here to here, and you label that with the letter L. And I've seen some people, not necessarily always has to be in there, but some people actually draw in the wave pattern as well that is vibrating, or the standing wave. So some people will draw that part in there as well. And that is absolutely fine. So there you go, guys. That is a full size diagram. It takes about roughly half an A4 page. All the labels in the correct places, all the correct arrangements there as well. Okay, so if we go then look at the second part of the question, it says, how did the student determine the length of the air column for a particular frequency? So let's just take quick note of the question. It's asking us, how did the student determine the length? It's not asking how did you record the length. Although we could maybe answer that particular detail as well, but it's asking you how do you know what length is appropriate to record when you actually are doing this experiment. So what we do, if you remember correctly, is that you submerge the, sorry, change that color, is you hold the tube in at a short length, in the water. Okay, so as much as is possible that you can hold the resonance tube in the water, you place it down into it. Then what you do is you strike the tuning fork. And hold it over the tube. And once you've done that, because your tube is inside the water, you then slowly raise the tube until a loud sound is observed. And when you have this part happening, that means that you have resonance with the air inside the tube and the tuning fork, which means you've now found the point that is appropriate for you to record the length of the tube. The next question then, for part 3, asks us, how did the student observe that what they heard was the fundamental frequency and not the overtone? So I've actually kind of mentioned this already in part 2, but I'm going to mention it again, and then I'm going to just explain to you why this is. So as we said in the first one, or in part 2, we hold the tube at a short length inside the water, and we increase the length until the first sound is heard. Okay. Now I'm just going to give you a diagram to explain exactly what that means. So I'm only going to draw the resonance tube and the tuning fork in this case. So I'm not going to draw the rest of the diagram. So you have to imagine that below the bottom of this is the rest of the tube. So let's just say I have my tuning fork, and my tuning fork is vibrating, and I can hear that sound. That means I have set up the fundamental frequency for this wave, which will be that shape. However, if I keep pulling that tube out of the water, what I'll end up with is this instead. So same tuning fork, vibrating, and what I'll end up with, and I'll just put a little mark there, I will end up with a wave pattern that looks like this. And what that is that is actually the first overtone of my fundamental frequency. So I have to make sure that I start off on the left with the length as short as possible, and then I pull my resonance tube up to make sure I get this fundamental frequency. And if I keep pulling the tube out, I will hear a loud sound again, which is my first overtone. So in order to ensure that you get the fundamental frequency, you start from a short length. Okay, folks, so the next question looks for us to make a graph. So if we go up and we look at the original question here, it tells us to use the data to draw a graph of f against 1 over L. Now, not every student in the country would do this experiment via a graph, and I think it can be a little bit more complicated, but they have told you in the question exactly what the graph is supposed to look like. So we know from doing the formula, we have C is equal to 4F bracket L plus 0.3D, where 0.3D is the error factor. The 0.3D tends to actually be quite small when you're doing these questions. So what I'm going to do is, for the sake of the graph, I'm actually going to get rid of it, because all it really does is it moves your start point. But in order for us to work out the speed of sound, we really just need the slope. So I'm going to just knock this off. And again, just what the difference does that make? It means you're going to have a graph that should look like this. By knocking that equation off, it just looks like this. But they do have the same slope, and the slope is really what I'm interested in here. So when I'm modeling this, that's how I'm going to use it. So that means the formula becomes C is equal to 4 times F times L. And I'm going to bring the L over. Right now the L is multiplying, so on both sides I'll make it divide. That cancels with that. Okay, so now my equation is C over L is equal to 4F. So that gives me, I'm going to swap sides over. 4 times F is equal to C divided by L. Okay, and if I bring the 4 over as well, that gives me F is equal to C divided by 4 times L. So what I can do here is I can factorize out this. F is equal to C divided by 4 bracket 1 over L. So on my equation, this now looks like a general form for a linear equation. So if I put my frequency values on my y-axis, and if I put my reciprocal values of my length on my x-axis, that means that my slope has a value of c over 4. So that means my slope is equal to c divided by 4. But what makes it even easier is the speed of sound in air is 4 multiplied by my slope. So that's why I'm doing this particular graph. Okay. So, again, that might always be given marks, but I always write that in because I think it's always important that you show what you're doing, and also it helps you model what you're doing when you're drawing up your graph. So I'm just going to change this now to graph paper. Okay, so here we have it. And I'm just going to make that graph paper a little bit smaller so I can draw a better size graph. So the first thing I have to do, like it said in the question, is I have to make a table that shows f versus 1 over L. So I'm just going to draw my little table here. And I'm going to use the frequency values from the question. And I will use the reciprocal of the lengths in meters. So when I do that, that's going to give me my values for f is equal to 250, 300, 350, 400, 450, 500. And my reciprocal values for length in meters is going to be equal to 2.94, 3.53, 4.17, 4.88, 5.24, and the last one is 5.88. So now that I have those values there, I can put them on a graph. So if I remember, my f values are going up as far as 500, and on the y-axis, my length values are going across as far as 6 on the x-axis. So what I'm going to do is I am going to draw my graph, and again, full A4 page. I don't know how well that's going to translate onto this screen. So let me see, I have 1, 2, 3, 4, 5, 6, 7, 8. 8 by 50 goes up in 4, so I might be able to get another 2 in there on this particular little screen here. So if I move down again by 2, okay, so that should give me 0, 50, 100, 150, 200, 250, 300, 350, 400, 450, 500. So I can just draw my x-axis going across. And again, I can draw these in my 1 over L. So 1, 2, 3, 4, 5, 6. Now the point of your graphs, guys, is they need to be as big as possible. So that should be done on an A4 page. Okay, then as per usual, I'll just start plotting those numbers in. So frequency, and that has a value of hertz, 1 over L, and that has a value of meters minus 1. So my first point is 2.94. So I come across and I count across all the little boxes. So 2.94 is just here. And if I move up, that goes to 250. And I usually put a little data point there and I put a circle around it to bring my eye to the data point. The next one is 3.53. So come across there. That goes up to 300. The next one is 4.17, which is just count the little boxes just over here. Then I come all the way up, and that is my 350. And the next one is 4.88. So come across to 4.88, up, and that goes to 400. Next one we come across is 5.24. 5.24 is just there. Come up to the 450. The last one is 5.88. So come across, go up to 500. That is my point there. So then what I do, take a ruler, and as per usual, guys, it's a line of best fit. Line of best fit is the line that fits as much as it can. Now my line of best fit just happens to go through 0, 0 mark. That doesn't necessarily mean it's always going to, and your line might slightly not. So that one there is absolutely fine. So as we can see, 1 point on the line there, another point on the line there. These three are slightly below. This point here is slightly above there. So just to not knock down on the line, a few below, one above. So that one's absolutely fine. So when I'm doing a question like that, I get 3 marks for labeling my axes. I get 3 marks for plotting my 6 points correctly. I get 3 marks for a straight line with good fit. And I also have 3 marks for having worked out the table just above right there. So that is a total of 12 marks for that particular question. Okay, folks, the next question was part 5. And it told us to find the slope of the line. So because it tells us to find the slope of the line, we are going to put in our details to get ourselves all the marks. So the first thing, m is equal to y2 minus y1 over x2 minus x1. Just to be aware, some students are in the habit of writing rise over run. You do not get marks for writing rise over run. You have to write y2 minus y1 over x2 minus x1. What you then need to do is you need to make sure you pick 2 points from the graph. And they have to be on the line. What I tend to do is I tend to pick 2 points that weren't the data points, and I try to avoid 0, 0. That said, doesn't mean you have to. You can pick 0, 0 if it's on the line, but I always just try to pick 2 points that are not. So I picked these 2 red points here, 178 and 2, 165. So I'm just going to write these numbers in here. 1 and 78, and the other one was 2, and it was 165. So I label them as per usual, x1, y1, x2, y2. So that's going to give me my slope is equal to 165 minus 78 over 2 minus 1. That's going to be a nice easy one because that's going to make my run, or my x2 minus x1, have a value of 1. And when I subtract the top numbers there, that gives me, just let me check, calculator, 165 subtract 78. That gives me a value of 87. Okay, so my slope is equal to 87. Where did the marks go for? You got 2 marks for this part here, 2 marks for your substitution, and then 2 marks for getting an answer that was roughly 85. So as you can see, we got the number 87. That is absolutely fine. Last part of the question, just label it and come back up to it. We can see is hence or otherwise calculate the speed of sound in air. I'm actually going to show you the 2 ways you can do this, because if you couldn't do this by using the graph or by using the graph, yeah, there's another way you can do it. We said already from earlier on that the slope was equal to c divided by 4, or the speed of sound is 4 times my slope. So the speed of sound in this case is 4 times 87. And when I multiply 4 by 87, 4 multiplied by 87, then my speed of sound is 348 meters per second. Okay, and that's close enough to the 340 in the question, in the marking scheme. Another thing you could have done is, if you didn't get your graph, you could have said that c is equal to lambda times f. So they have given us the frequency in these questions, and they've given us 1/4 of the wavelengths. So what I can do is I can take one of my lengths from the question. I'm just going to take the first one, which was 34 centimeters. So my wavelength is 4 times the length, because of the fact that we are using a 1/4 of the length of the standing wave to, 1/4 of the wavelength makes up my standing wave for this one. So that means c is equal to 4 times the length. And again, the first one in this particular question was 34 centimeters, which is 0.34. And if I multiply that by the first frequency, which is 250, if I multiply all those numbers out together, that can also give me an approximate speed of sound. So 4 multiplied by 0.34 multiplied by 250 gives me on the button of 340 meters per second. So depending on which way you were able to address the question, you could do both questions and got full marks in that particular manner.